Okay, so to calculate the energies of the electron, the allowed energies of an electron in such a sort of planetary model, we start with Newton's second law. Okay, basically that's a good place to start almost anything. We start with F equals ma. Okay, and so here, right, the force to obtain a particular acceleration is the constant of proportionality between the force and that acceleration is just the mass. So in this case, the force that we're talking about is the Coulomb force, and the mass is the electron mass, and the acceleration is going to be the centripetal acceleration as the electron goes around in the circular orbit. Now, implicit in this, in what I've just said, and in this picture, is that we're assuming that the nucleus is stationary. Okay, and it turns out, and that the nucleus is stationary, the electron is the only thing that moves, and it turns out that that is a good approximation when the nucleus is much heavier than the electron, and that is essentially always the case because a single proton has a mass something like 2,000 2,000 times more massive than an electron, and so the center of mass is actually very close to the nucleus. If we had some sort of other similar system, a positive and negative charge, as you'll be considering in your homework, where the masses are more similar, then we'd have to consider that both bodies rotate about their common center of mass. But here we're assuming that the nucleus is stationary. Okay, so if we so the centripetal acceleration, if you remember from your mechanics class, is v squared over r. Okay, and so the Coulomb force between two charges is 1 over 4 pi epsilon naught. Again, this is the permittivity. Epsilon naught is the permittivity of free space, times the product of the two charges, which in this case is ze times e, divided by the square of the distance between them. Okay, and again, we set that equal to the mass times the acceleration v squared over r. Now, we can cancel this r with one of these, and what we notice is that the right-hand side here, mv squared, looks very much like the kinetic energy. We just have to multiply by half. Okay, so the kinetic energy is equal to 1/2 mv squared, is just 1/2 of this on the left-hand side. So it's 1 over 8 pi epsilon naught times ze squared over r. Again, z is the atomic mass, is the atomic number of the nucleus. Okay, so if it's just a hydrogen, then z is equal to 1. All right, so this is the kinetic energy, and so we can then calculate the total energy of an electron orbiting the nucleus. So it's the sum of the kinetic and potential energies. So again, the kinetic energy is what we wrote down on the previous page, and then the potential energy is related to the Coulomb attractive force, but and so it's the integral of that force, and so what we find is that it's minus 1 over 4 pi epsilon naught ze squared over r. So it's, instead of, for the force we have an r squared, here we have an r. Okay, and so if you add these two things together, that you get the total energy of the electron in this simple planetary model, the allowed energies for the electron, and the relationship between the energy of the electron and the radius is this. It's minus 1 over 8 pi epsilon naught times ze squared over r. Now, what range of energies can the electron have using this expression? Well, if r is equal to 0, that is if the electron basically crashes into the nucleus, then this term goes to infinity. So you have that the energy of the electron is equal to minus infinity, and at this point the model breaks down. Okay, the model doesn't really work. That's unphysical. So the model doesn't really work for that case. If r is equal to infinity, so if you take the electron out and separate it from the nucleus by an infinite amount, then you have the energy is equal to 0. Okay, and this means the electron is just now separated far. You have to go to infinity basically to unbind the electron.